last time. So last time we stopped at this example. We were basically trying to describe the power spectral density. Define the power spectral density to be the Fourier transform of the autocorrelation function. And we said that why we do that because we don't have mechanistic signal mechanistic signals. We have a signal, we get the Fourier transform, we get the frequency compensate, we get magnitude square, we get the power, how power distributed among different frequencies in mechanistic signals. But in random signals, random processes, we don't have a signal to take its frequency because that's the only thing that describes the relationship, how fast the random process changes, is the autocorrelation function. And this is basically, if we take the Fourier transform of the autocorrelation function, we do what we refer to as the power distribution. And you see that it's a density function, means that it gives you how is the average power of the signal distributed among the different. This should enable us to be able to filter and process the signal. And the inverse Fourier transform of the power spectral density is the autocorrelation. So they are basically tied with the Fourier transform as a Fourier transform there. And we have several examples on the properties of the power spectral density. And then we stop basically at this particular example. And we basically where the autocorrelation function was given. And the question was find the power spectral density. And then find several other things. Compute the average power in the low pass part and in the band pass. Low pass around 0, band pass, which is basically unhigh. So in order to find the power spectral density, we have written the Fourier transform. So basically, the autocorrelation function was expanded in terms of as basically 4 different terms. One term, which is a DC value, and 2 other terms which are a little bit higher frequency. So we have the 3 terms multiplied by the E exponential of minus W absolute value tau, and then the Fourier transform part. So basically, we expect that the power spectral density will contain how many parts here? 3 parts. We have 3 parts, 3 basically parts to be taken the Fourier transform with spectrum, and every one will give you 1 item. So the first item here is half E to minus W absolute value tau, and then the Fourier transform. And it's given to you. Well, you know how to find this. Oh, but it's basically given to you. As you mentioned, we try to avoid giving examining you on process and finding the details. So we try to help you as much as we can by giving you any details. Not to make mistake in the details. So if we look at the Fourier transform of half the exponential, then it will be basically this part on this side. And then if we look at the next item, which is 1/4 e to minus j 2j omega 0 tau, multiplied by the exponential, and take the Fourier transform, we give you this part. And the last part, try to do it using this idea by combining the exponential with the Fourier transform. Will be basically nothing but a shift. So if you look at these 3 terms, which one of them is around 0 frequency, and which one of them around some carrier frequency? This is around 0. If you put it, you will see that it's basically this part. Okay, so this is the first part, which is around 0. It's dw divided by w square plus omega square. This is the low pass. And we call this as the low pass. And the other 2 parts, the green ones, as you can see here, there is a shift at 2 omega 0, and there is a shift at minus 2 omega 0. So this is the shift at omega 0, 2 omega 0, and this is the shift at minus 2. We call these as band pass components. Okay? Band pass. Band component. transparent. Okay. Components. So the other question, so basically this is the power spectral density. Now in order to find the power in the low pass, how much is in the low pass? Simply you need to integrate the low pass component from minus infinity. Basically you take the area and the decay. And if you do that, you will get basically V1. And in order to find the power in the band pass, the power احنا قلنا ايش في the area and the decay of the spectrum of the power spectral density. So integrating this part along with this part will give you another V over Q. You can see that this signal has 50-50 of its power around the zero frequency and around the or two on this. Thanks, any questions? How to find the power spectral density from the what is the relationship of the average power with the power spectral density? It's the area. Okay. Now let's talk about another example, meaning the white noise. Now the white noise is very important concept. As you mentioned before, when you deal with electronics, communication, electronics, and signals, any type of electrical engineering kind of processing, you will have to deal with the signals signals move through the different components of these electrical components basically get the safety, and as they safety, they make electrons move, and while they move, they produce some noise. Now the noise looks like the power spectral density of the noise looks like this. It's an equation that you don't need to worry about the details of it. However, if you plot it, you will find that it is peak at zero frequency, and it goes very, very slowly, decays very, very slowly, such that it is almost 0.9, the max. So at maximum here, the maximum value is N over 2. And after almost 1000 gigahertz, which is 1 terahertz, it's almost 0.9 the maximum. You can see that it becomes extremely very low. What does this mean? It means that it's a very, 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 very wide band noise. So 1 terahertz. 1 terahertz means 1000 giga, means how much? How many gigahertz? 1 million. So it's even after extremely high bandwidth, still the power spectral density is at very large value compared to the maximum. So it doesn't decay. And this is why we call such a noise as white noise. Why do we call it white? Yeah, but why? For instance, we could call it black. Why white? Red. Why white? ايش رايكم يا شباب؟ ايش الوايت color? All the colors. All the colors. And what is the color? ايش هذا الكلام؟ Certain frequency. Exactly. How do you see the red color? ليش نأتي على الناس عندهم عمى ألوان? Because the filter in their eyes stop responding or detecting the frequency حق الكلر معين. So basically, every color in the visible light is a frequency by itself. The red is a frequency, the green is a frequency, and so on. And our eyes are equipped with camera, like filters, where basically the light comes here with our eyes, and we basically sense these lights by detecting these signals. So now, why we call it white again? Because it contains all frequencies, all colors. The white color contains all frequencies, all colors in the visible light, and because of that, we call this as a white noise. White noise because it contains all frequencies equally Yeah. So it contains all frequencies. You can see that the power spectral density is flat. Flat across all frequencies. Well, this is a theoretical PST. This is a practical. This is a major power spectral density from electrons. You can see that because it decays extremely slow, for all operations, for all frequencies of operations that we work with, until now, we so far the maximum frequencies that people work with is the millimeter wave, which is basically almost 50 gigahertz, 50 to 60 gigahertz. We are talking about up to 1,000 gigahertz still, because the density almost constant. So for us, for practical engineers, such a noise looks like is a white noise. And because of that, we call it white noise. As I mentioned, this is very common in many applications in electrical engineering, among which is communication data. Communication signals, control, and many things. So basically, the white noise, why do we call it white? Again, because it contains the power spectral density contains all frequencies equally likely. What does equally likely mean? It means that the amount of power for different frequencies is the same. As you can see, it's a flat power spectral density. Minus infinity to infinity. And this is an approximation of what I showed in the previous.
How do we filter?
One thing related to this is this something practical or theoretical? It's theoretical, however, it approximates very well the practical case. It approximates very well in the case of the Okay, this is almost constant, however, it's not constant. That is constant. Constant because it makes our life simple in many ways. So this is not a practical. If the white noise doesn't exist in practice, generated in now, you will never see it in the world. However, the noise that you experience in circuits is extremely close to the white noise. And because of that, we consider the white noise as something important to discuss. Now, if we take, this is the power spectral density. If you take the inverse transform of power spectral density, what do you get? What do you call this? Autocorrelation function. So the autocorrelation function, if you can see, it's a delta function. What does a delta function in autocorrelation mean? Measurement autocorrelation gives you the relationship between the signal and the delayed version. Right? So what does this mean? So basically a signal and a delayed version by even 1 nanosecond. They are totally unrelated. Which means that the signal, this noise, changes at an extremely fast rate. Such that even after 1 nanosecond from remove, the signal and itself, a delayed version of it by 1 nanosecond is what? Uncorrelated, non-amplified. So basically the signal moves at a very fast rate such that it's not correlated even by a delayed version with a very small time delay. نقول rate of change means what? Rate of change. Rate of change is a frequency. So very high rate of change is very wide. طبعا this is زي ما قلنا الوايت noise is not realizable. Is not basically realizable in a lab. You cannot generate it in the lab because it's very simple concept here. How much is the average power? ايش الافريج باور؟ كيف نجيب الافريج باور؟ The area under the curve, right? Of the PST. If we integrate the PST, we get the average power. So what is the average power of this? Infinity, because the area under the curve is infinity. And because of that, this is not something realizable. This is an approximation of well-known behavior in many systems. Okay? So although this is, you will not find a white noise in practice, but for the operation, for the value of operation that you are operating with, you will find that the noise is extremely wide band, such that it looks like. And because of that, we discuss it because, as I mentioned, although it's critical, within our operation, within the value of operation that we work with, it is very applicable and it looks white. And مهم جدا نفهم what does white mean and what is the corresponding relationship, what is the corresponding autocorrelation function, why is it impulse, what does impulse mean? طيب. So now, if we have a white noise and we filter the white noise, okay? Or basically, we have a band limited low pass white noise. What does that mean? It's a white noise within our band of operation. So within my frequency, within my bandwidth, the noise is loud. Right? So the PSD will look like from minus W to W as a vector function. Now, if we take the Fourier transform of this, what do we get? The Fourier transform of this, what do we get? The only one sinc function. So basically, you can see that the vector function will look like a sinc function. So the autocorrelation function will be a sinc function. What does it mean? It means that as W increases, it means that the value of the noise increase. So when W increases, what happens with the sinc function? It shrinks, basically. W, this is pi over W. So basically, as W increases, the width of the sinc function becomes narrower and narrower, which means that it changes at faster or slower rate? Faster rate, because the autocorrelation function is narrower, means that it's uncorrelated after a small amount of time, while if W is smaller, then basically the autocorrelation function becomes wider, which means that the signal changes on average at a lower. Okay? Now let's talk about the band pass. So again, if we are operating with a baseband communication, if we are working on a band pass communication, then basically the signal will look like, the noise PSD will look like concentrated around omega 0 and minus omega 0. So these are, omega 0 is, we call it here, the carrier frequency, right? Carrier frequency. And the noise will be minus width W around the omega 0. Again, in the PSD in mathematics looks like this. Now, if you take the Fourier transform, you will get a sinc function modulated by a cosine. So it's a sinc function. This is the sinc function. Inside the sinc function is the cosine. Okay? So this is the sinc function. And this is the cosine. And if I change W, what happens? If I increase W, what happens in the autocorrelation function? What is shrinks? What shrinks is the sinc function. The sinc function becomes normal. However, the inside cosine will stay the same because I did not change omega 0. The inside cosine changes with omega 0. The envelope changes with the sinc. So if I change W, if W increases, the sinc becomes narrower. Okay? Or if W decreases, the sinc becomes wider. However, if I keep W the same, which is the value of the noise, and I change omega, the sinc will stay the same. However, the frequency of the cosine will be, the inside cosine will be. And let's end with an example on, again, the relationship. Could the chapter have about the relationship between the autocorrelation function and the power frequency? How to find this from that and that from this. So here, this is the autocorrelation function. It's given by this function, which if you plot it, it will look like this exponential and the exponential in the two. positive and the negative. So you can see here that the autocorrelation function clearly decays as tau increases, which is expected. So now, if I change 3 here, if I make it 10, what happens to the autocorrelation function? If instead of 3 we have 10, what happens to the autocorrelation function? It decreases faster. Basically, it becomes narrow. Now, if we take the Fourier transform of this, using this relationship, you will find that the Fourier transform of the PST will be given by this. And plotting it will look like this. So clearly here, if instead of 3, I have 10, this becomes narrow, right? What happens to the PST? Becomes wider, because instead of 9, I will have 100. So this becomes 1. I guess it is short. Basically, this ends chapter 7. Again, most of what we have done in chapter 7 was the relationship, how to understand article C's in that we defined a very simple or a very key result, which is the power spectrum, which as the autocorrelation function previous. تقريبا هذا هو اللي سويناه كله في chapter 7. Now in chapter 8, again chapter 8 will be a short chapter like chapter 7 or even shorter. What we'll try to learn in chapter 8 is, now I have a random process exciting an LTI system, linear time invariant system. I will get now interactive input. Okay, if I know the characteristics of the input random process, how do I know the characteristics of the output random process? Characteristics means the mean function, the autocorrelation function of the input. إذا عرفتها, how is this related to the mean function, the autocorrelation function of the output? If I know the autocorrelation function of the input, I know the PST, right? I need to know the PST as well. So this is a typical kind of signal processing application. If your signal is random and you are inputting it to a linear time invariant system, how the output will look in time domain and in frequency domain. So this is all chapter 8, and it is, as I mentioned, this is a short chapter, so we're not consuming a lot of time while this lecture and next lecture. Well, these are the key results. We come to it. How did we find it? Aisha, are you clear where we are here? So in chapter 6, we learned everything about time domain analysis of random MCs, autocorrelation and the mean, and we talked about the right sensation and so on. And in chapter 7, we understood the frequency content of random interest. Here in chapter 8, we will understand how to, if we process a random group, we filter a random process using an LTI filter, what do we do? So in order to be able to do that, we'll just review the basic linear time invariant system. If I have an input, x of t, and I get an output y of t. These are specific waveform, I get a specific waveform, right? And because this is an LTI system, how is y of t connected to x of t? Convolution. So basically, y of t is the convolution of the system impulse response and x of t. What is the system impulse response? H of t. What does this mean? When you say impulse response, what does it mean? What are the characteristics of the system? What does it mean? Exactly. When we excite the system with an impulse, we get at the output. Okay, this is in time domain. In frequency domain, if I excite the system with a white noise, complete white noise, means that white, means a flat a signal that contains all frequencies, I get H of t, which is the frequency response, right, of the system. So if this is H of t, then we have in the frequency domain S8 H of omega. We call this as S8 تذكروا transfer 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 function means that how the frequency here is created in the system such that we get it. طيب. Now, this is if I have a waveform at the input, I get a waveform at the output, that is convolution. Like, what about if I have a random process? Not a waveform. Random process is a set of different many waveforms. Every time I repeat this experiment, I will get one of these XOPs. So the output will be a convolution, but I don't have a specific function to convolve with. So I really don't have a specific waveform at the output. Because the input is random, the output will be one. Also, okay, so this is the first thing. So since this is random process, this also will be a random. Now, what is left in this chapter is to try to relate the mean at the output, the mean function, with the mean of the input. The autocorrelation function of the output with the autocorrelation function of the input. The power spectral density of the output with the power spectral density of the input. This is what we're trying to do. Okay? طبعا في بعض الاشياء هنعطيكم result like this and في بعض we derive it. So yes. So and we also will focus only on white sensation. With the input is white sensation. So we have an API system and the input is only white system. This is simple. And assuming that everything is contained, basically everything doesn't blow to infinity, so we have specific power, so nothing basically goes out to infinity, then we can exchange expectation and integration. Now, the mean function of y of t, the mean function is simply we just replace what y of t is. Y of t is the convolution of x of t and the input systems, right? And since everything, as we mentioned, doesn't go to infinity, then we can input the expectation inside, because the integration is nothing but a linear summation. So it will be the integration of h of t with the expected value of x of t minus condition. Now, if you can see here, since this is white sensation, how can we describe the mean function? Well, it's a number. The mean function is nothing but a number. Constant. Because of white sensation. And because it's constant, equals x bar. We can take it out. And here we have it at x bar. Okay? X bar multiplied by the area under the curve of which is another constant. So if we have a white sensation at the end of an API system, we get the mean of the output will be also constant. It's basically the mean of the input multiplied by the area and the whatever that. Just integrate it with h of t on 9 centimeters. So this is the first thing, the first result. Now the second result, we talk about the mean squared. Mean squared عبارة عن ايش؟ خلينا نتكلم على الباور. ايش علاقة المين سكوير بالباور؟ 60 power. This is the average power. So expected value of y square of t. Again, we just replace y of t. So it will be 1 integral multiplied by another integral. And because we have two integrals, we define lambda1 and lambda2. Okay? Now the rest is just reordering things. First of all, ندخل expectation داخل. And we put everything that is random inside the expectation. And everything that is not random outside, which is the two impulses functions. And we have two variables here. So here h1 lambda1 and h of lambda1 lambda d lambda1 and h of lambda2 d lambda2. And we have lambda1 and lambda2 inside. Okay. So what is this expected value of this? Let's see. Auto correlation, right? It's the autocorrelation function of this time minus this time. So if you take t minus lambda1 minus t, يعني بين قوسين t minus lambda2, you will t cancels t and you have autocorrelation function of lambda1 minus lambda2. Right? Multiplied by the two impulses. So basically the mean square value will be equal to, which is the average power. By the way, this is equal to what? Let's go average power. It's equal to Rx, Ryy of 0, right? And we said that this is equal to, again, the integral of the Sxx of omega d omega. Why do we call it average power? Because it's the area under the curve of the PSD. The autocorrelation function at 0 equals the area under the curve of the conflict with density. And this is equal to the average power, right? And because of that, this is important. Expected value of y squared is important. It's the average power. Right? So we find that the average power is nothing but a double integral of the autocorrelation function multiplied by the two impulses. If you are lucky, it's easy to find. If you are not, it will be difficult. So this is it. No close answer. Now, for white noise, fortunately, this is a very simple thing to do. For white noise, the autocorrelation function is what? White noise, which autocorrelation function? It's a delta. So the autocorrelation function of lambda1 minus lambda2 is nothing but n naught over 2 multiplied by delta of lambda1 minus. Now, writing this autocorrelation function, substituting it in the previous equation, you will have basically a delta function multiplied by h1, h of lambda1, h of lambda2. And we know that if we multiply a delta with one of these integrals using a shifting property, this will be, if we take delta of lambda1 minus lambda2 multiplied by h of lambda1, this will be equal to, and integrating will be h of lambda2, the location of lambda, right? So we'll have h of lambda2, and one of the integrals has been done. So this will be the integration of h squared of lambda2, and multiplied by n naught. What is n naught over 2 here? As well? It's the level of the PSD. So if this is Sxx of omega, this is n naught. Right? Why do we call it n naught over 2? Because it has many other relationships of communication. So this is n naught. It's the level of the noise. Alright. So basically, we get the average power Pyy of the average power of y is equal to the area under the impulse response squared multiplied by the input average power. So for white noise, the output power is proportional to the area under the square of each. Whatever that is. Now, what we did here is we found the average power, now which is Ryy of 0. Now let's find Ryy of tau, which is the general thing. This is the expected value of y y of t plus tau, and repeating the same as what we did here. الفرق ايش حيكون هنا عندك؟ بدل y square y of t multiplied by y of t, you will have y of t multiplied by y t plus tau. So the other term here will have plus tau here. So it will be y of t plus tau. So it will be plus tau. So here it will be again tau. So what we get is similar result. However, Rxx of tau. This is the difference between the previous and the previous. Multiplied by the other two. The same. So if you look at this, if you look at one integral only, and assuming lambda 2 is just a constant, what do you think? What is this? What is this? H convolution of H with the autocorrelation function, right? Now, if we look at the other, we look at H of lambda 2 and ignoring lambda 1. What is this? Again, a convolution, but convolution with a negative sign. So there's a minus. So it's a two-fold convolution. So Ryy of tau will be Rxx of tau convolved with, first time with H of t, the second time with H of minus tau. H of tau, H of minus tau. Because if we ignore lambda 2, it's a convolution, right? If we ignore lambda 1, what do we have? Convolution, but we have a negative. And because of that, we have a negative. So the output autocorrelation function will be double convolution of the input autocorrelation function with the impulse response and the version of the impulse. Right. So what do we get? Nobody will ask you to do double convolution. Until now, nothing is interesting. هنا double convolution ما حد حيسألك تسوي double convolution. هنا okay, fine. هنا جالك integration معقد. Again, nobody will ask you to do that. So until now, nothing is useful except for the white noise. So let's try to find some useful information. إذا كل الأشياء تعطيكم إياها معقدة. Okay, let's try to find something that is easy to. So until now, we have the mean. Easy to find. It's the mean of the input multiplied by the area. We have the mean square, which is the average power. Okay, it's given by this autocorrelation function multiplied by the. And we have for white noise specifically the average power of the output equals the input in not over 2 multiplied by the area under the curve. And we have the autocorrelation function of the output equals the double convolution of the autocorrelation function of the input twice with the impulse response. Again, ما هي مفيدة بشيء. خلينا نشوف السبيكترال كاركترستكس. يعني سوف في التايم دومين الشيء الوحيد اللي ممكن نحسبه المين والاوتبوت باور if we have white noise. The rest is complicated. Okay, let's try to see. Okay, in time domain, these are the only two things that we can calculate. Let's see in frequency domain how things will simplify. عشان كده الفريكونسي دومين دائما مفيد because it gives you another way to simplify things, to analyze things. So now let's take the Swedish power attendance. Let's take the Fourier transform of the system. Okay, again assuming x of t is white stationary, so the input is white stationary process. Then y of t is also white stationary. By the way, احنا ما تكلمنا عن هذا. لو تلاحظوا في شيء نحن قلنا الانبوت is white stationary, right? What about the output? ايش رايكم؟ ماشي معك. الانبوت was white sensation. What does white sensation mean? The mean is constant, right? The autocorrelation function depends on time, doesn't depend on t. Right? But what about the output? What was the mean of the output? Constant. We found that it's constant. What about the autocorrelation function of the output? Does it depend on time? Do you see t here? So you can see from the autocorrelation function of the output that it does not depend on time. And because of that, y of t is what? Is also White sensation. So the key result here is that if the input is white sensation to an API system, the output will be also white sensation. And at least something really. Right. Well, let's talk about from frequency perspective, from frequency domain perspective. How can we analyze things? So the input is white sensation, the output is white sensation, and so something that we did not talk about is that also the input and the output are jointly white sensation. Means that the cross correlation function is also not a function of time. Now let's talk about the power spectral density. Now the power spectral density, again, we'll not divide it here, but you can easily find it from this result. The autocorrelation function of the output is the autocorrelation function of the input double convolution. Now, if you take the Fourier transform of this, what do you get? The PSD of the output. Now, if you take the Fourier transform of the right-hand side, you have two convolutions. How convolution change into frequency? It will be product, right? So it will be so basically taking the Fourier transform of this. What do you get? You get SYY of omega, right? صح? And taking the Fourier transform of this, what do you get? أول واحد إيش؟ Yeah, the power spectral density of the input, right? And the two convolutions will change into multiplications. Multiplication with what? What do you multiply here? H, if we take the Fourier transform of أول واحد, what do we get? Capital H of omega, which is the transfer function. And if we take the Fourier transform of this, what do you get? The conjugate of that. The conjugate of H of omega, right? So this will give me H of omega conjugate, H of omega, right? واضح شباب؟ But what is H of omega conjugate? Magnitude square. Exactly. Magnitude square. So the output spectral density equals the input power spectral density multiplied by the magnitude square of the linear time event system. هذا سميناه ايش؟ H of omega سميناه transfer function, right? Transfer. Why is it transfer function? Why do we call it transfer function? Because y of omega, sorry, equals اللي ما كان عنده random process. Y of omega equals x of omega multiplied by h of omega. So if I want to see every frequency as the input, how was it treated? كم صار الامبليفيكيشن ولا phase shift؟ ايش اسوي؟ لكل frequency اضغط في h of that omega. I get what happens in the output, right? And because of that, we call it transfer function. It transfers every frequency from the input to the corresponding value in the output. Here, what do we call this? Power transfer. Exactly. Power transfer. Because it doesn't tell you how the voltage changes for every frequency. No, it tells you how the power from the input changes to the output for every frequency. And this is a very important result, because it tells you how is the randomness and the input was filtered, how the frequency contents change from the input to the output. واضح؟ لكن هذا ملخص اللي سويناه هنا. Now the average power is what? Is the area under the curve of the average power of the output? Is the area under the curve of this y1, which is the PSD of the output, which is this. تتذكر الكومبليكيتد اكسبريشن اللي طلعناه هناك ايش كان؟ وين هذا؟ This was the average power, right? This was the average power. Double integral framework. بينما هنا it's very simple. It's the area under it. It's the area under it of the output. What is this? What is this? ايش سمينا هذه الصورة؟ S Y Y, right? So if I have an input x of t with an impulse response y of t, and the impulse response, the transfer function is h of omega, then Sx x of omega will be transferred into Syy of omega, which is equal to Sxx of omega multiplied by the power transfer function, which is the transfer function magnitude square. And the next slide is the proof. How did we do this? I already did it for you, so no need to worry about it. So this is already covered. So basically, we are almost finished. So basically, we are left with several examples. Next time, inshallah, we'll talk about them. 3 or 4 examples. And after that, we'll move to the statistics part. Yes, Ursula? So by this, we are done with the mobility part of TQ2. We are left only with several examples. We'll cover this one. And next time, we'll start with the statistics part. Hopefully, it will be a different perspective than probability. That they are connected together. And it's a very important part for your diagram. Right. Any questions about? So next time, inshallah, see you. By the way, we have a quiz next. Okay. It will be the last quiz, and it will be about chapter 6, 7, 6 and 7. Okay. Thank you very much.